Okay, this is the last installment in the effects of atmospheric pressure on your exercise responses. And this section has to do with exercise and what happens when you are diving. So when you're diving, you have an opposite problem that you experience at altitude. So at altitude, the problem was hypobaria, which caused hypobaric hypoxia. When you're diving, you actually get an increase in atmospheric pressure. So the pressure that you experience while you're diving increases by 1 atmosphere or 760 millimeters of mercury for every 10 meters that you dive underwater. So at sea level, your atmospheric pressure is 760, and every 10 meters you go down, it increases by 760 millimeters of mercury. The problem with that is the first problem is diving just from the increased pressure or the weight on your body. This causes a decrease of volume for different cavities in your body, and this includes the volume of your middle ear, your lungs, and your sinuses. So when they're under pressure, the volume of those spaces decreases. And you'll notice this if you dive in a swimming pool. If you just go to the bottom of a deep end of a swimming pool, sometimes you will get an earache, and that earache is caused by this increase in pressure and the decrease of volume in your ear. The most hazardous situation can happen when you're scuba diving, and you can get damage to your lungs if you don't expire your air while you're ascending from the dive. So what happens is when you're at depth and you inspire and you fill up your lungs, so your lung volume's increased, if you don't blow out your air while you're ascending, the decrease in pressure will cause a further increase in volume of your lungs, and that can cause your alveoli to burst and result in serious lung injury that can often be fatal. So the guideline when you're ascending from a dive, when you're coming up from a dive, is to exhale your air and to exhale so that you're forming bubbles in the water that are rising faster than you are ascending from your dive. Another problem with diving is gas toxicities. So as you know, the air that we breathe is mostly made up of nitrogen. So 79% of the air we breathe is made up of nitrogen, and about 21% of the air we breathe is made up of oxygen. When these gases are under pressure, they both cause toxicity to the tissues in your body. So when oxygen is under pressure, you get formation of what are called free radicals, which are molecules that increase damage to your cell membranes. When nitrogen is under pressure and driven into your tissues, especially your nervous tissue, so for example, your brain, it causes an analgesic effect. So it would make you feel like you've had a few glasses of alcohol. So it actually makes you feel drunk, and this can impair your performance while you're diving, and this is called raptures of the deep. And so when you're scuba diving, they often fill your scuba diving tanks up with helium to replace some of the oxygen and nitrogen that's normally in the air, to prevent these toxicities. So you still have a certain amount of oxygen in your tanks because your body depends on oxygen for survival. But the amount of oxygen is reduced to prevent oxygen toxicity, and it is replaced by helium. So scuba diving tanks usually have a reduced percentage of oxygen in the tanks. The question here is, why can oxygen requirements of the body be maintained if breathing a gas mixture of less than 21% from scuba diving? And the answer here is that if you're under pressure from being under the water, the partial pressure of the oxygen in your tank is maintained even though the percentage of oxygen in the air is reduced. So you have to go back to this equation that I have on the whiteboard. Partial pressure of oxygen is equal to atmospheric pressure multiplied by the percentage of oxygen in the air. So within your oxygen tank, they will reduce the percentage of oxygen in your tank and replace that with helium to prevent oxygen toxicity. And your PO2, so that's the pressure of oxygen from the tank, is maintained because underwater, the atmospheric pressure is increased. So the pressure of the water increases the atmospheric pressure to offset the reduction in percentage of oxygen in your scuba diving tank so that your partial pressure of oxygen and that driving pressure to get oxygen into your lungs is maintained. So another problem with scuba diving is called decompression sickness. And this again occurs if you are ascending too rapidly from your dive. The nickname for this is called the bends. And it's called the bends because about 100 years ago, when they first started doing industrial work underwater, for example, working on the base of a bridge, when the workers came up from the depths too fast, they experienced very severe pain in their joints, and it actually made them bend over in pain. So they nicknamed this condition the bends. The formal name for the condition is called decompression sickness. This happens because at high pressures, for example, when you're diving, nitrogen is forced into tissues. And then if you ascend too rapidly, the nitrogen leaves your tissues and forms bubbles in your blood. And these bubbles can cause pain in your joints, and they can also cause blood clots that hinder the blood flow through your arteries. So this can be fatal if, for example, you have a blood clot leading to your lungs or leading to your heart. So the strategy here is to ascend slowly so that you don't get this rapid formation of bubbles in your blood. This can also occur if you are rapidly ascending to altitude. So if you are scuba diving, it's not a good idea to fly in a helicopter or an airplane on the same day. And it's not a good idea, say, to climb a high mountain on the same day that you're scuba diving, because it can make this effective decompression sickness worse. And so when you're diving, you have to spend time decompressing when you come up from your dive. So in other words, you have to take stops while you're ascending, or you have to ascend very slowly to prevent the decompression sickness. So this depends on the depth and the duration of your dive. So the deeper you go and the longer you dive, the longer you have to take with your ascent to prevent this condition. So when you go scuba diving, they have charts that tell you the amount of time you have to spend ascending depending on the depth of your dive and on the duration of your dive. Exercise can affect your level of decompression sickness. And so if you exercise while diving, it makes the situation worse. And this is because there's an increase in blood flow to your tissues and an increase in nitrogen delivery to your tissues. But if you exercise 24 hours before you go scuba diving, studies have shown that it reduces the amount of bubbles that are produced during decompression. So it actually makes the situation better, and it can alleviate some of the decompression sickness. Now, other exercise responses you get when you're diving is that you get an increase in oxygen consumption or energy expenditure at a given submaximal workload when you're diving. This is due to a number of factors, including the increased work of breathing, an increased shivering if you're diving in cold water, and also increase work of moving against the pressure of the water. So water obviously offers more resistance than, say, air, especially when you're under a lot of pressure if you're at very deep depths. So the work of breathing increases while you're diving because when gases are under pressure, they become denser, and it just makes it more difficult to move those gases through your airways. So there's greater increased resistance in your airways and makes the work of breathing harder. So what happens to the blood flow to the legs during weightlessness? So this occurs if you're underwater, and it also occurs in astronauts if they're exposed to microgravity. So essentially what happens is that the blood flow goes from your legs to your upper body, and this will have the effect to increase venous return to your heart and increase your stroke volume, and in turn decrease your heart rate to keep your cardiac output consistent. So at a given exercise intensity, you'll have a lower heart rate in the water and an increased stroke volume. And this is just kind of a bit of a tangent. If they're doing ground-based experiments to simulate space flight, they put someone in a bed rest position in a head down tilt. And that's to force the blood flow to go from the legs to the upper body. And that's what you experience in microgravity, and also what you would experience if you're submerged in water. There are some strategies for increasing breath hold duration, and this is important for some occupations that might involve free diving. So in other countries, they have some free diving occupations that involve, say, collection of oysters. And so the longer that they can hold their breath, the more oysters they can collect, and the better they can perform their work. And so there are some strategies to increase the duration of your breath hold. That includes hyperventilation, breathing gases with higher oxygen content before the breath hold, and also breath holding on land before you actually breath hold in the water. So when you breath hold, apparently it increases contraction of the spleen, and that this increases release of red blood cells into your circulation. This would increase your hemoglobin content and increase the oxygen carrying capacity of your blood, increasing the oxygen delivery to your tissues. It's generally not recommended to use the strategy of hyperventilation to increase your breath hold duration. It can be dangerous, and this slide outlines why it is dangerous. So hyperventilation is effective for increasing your breath hold duration, because when you hyperventilate, you blow off carbon dioxide, and it's the carbon dioxide that drives the ventilatory centers in your brain. So it drives your need to breathe, and so it increases your ability to hold your breath if you're underwater. But the hazard is that while you're holding your breath, the percentage of oxygen in your lungs and in your blood is rapidly decreasing as your muscles continue to use the oxygen. And this might be okay at depths, because at depths, recall that your partial pressure of oxygen in your lungs and your blood depends on your atmospheric pressure and the percentage of oxygen that's in your lungs and your blood. So while this is decreasing, this would still be high when you're at depth. And so the high atmospheric pressure you get at depths can offset the decrease in percent oxygen that you have in your lungs or your blood. And that will keep your PO2 constant for a while. The problem is when you come up from the dive and you're in shallow water, you get this decrease in pressure, and that's going to decrease. Because your atmospheric pressure is now decreasing when you're in shallow water, you get a dramatic decrease in PO2 of your lungs or your blood, and that's going to make you hypoxic. And so a problem that people have when they come up from a breath hold dive is called shallow water blackout, in that you might have too much of a decrease in PO2 when you come up from the dive and you're in shallow water. And so what happens often is people will pass out when they're in the shallow water as they've come up from a dive, because of this decrease in pressure, decreasing the partial pressure of oxygen that's in your lungs. So to summarize, at a high depth, the PO2 in your lungs can still be high despite the reduced percentage of oxygen in your body, because PO2 depends on your atmospheric pressure, which is high while you're at a depth, and that offsets the decrease in percentage of oxygen in your lungs. But as you ascend, the pressure is decreased, and that results in a decreased PO2, and this can lead to that condition of shallow water blackout. So that's it for my lecture. I've posted my email address here in case you have any questions, and I will answer your questions via email, and I will collate any questions from the class and the answers for the rest of the class. And I'll post that on the Blackboard system.